Hi, this is Manuel with Intagma. Today I want to dive into some abstract art stuff by doing a Voronoi surface treatment, or as I call it, a dual surface. Why dual? Because we are using the dual graph to a delaunay triangulation. So what does that mean? Let's first look at the diagram. On the left you have a delaunay triangulation. It's just a triangle mesh basically with some rules applied such that the interior angles are in a certain way. The details do not matter here, but if you have this triangle mesh, what you can do is to just find the barycenter of every polygon, as I indicated here on the right. And if you now connect these barycenters, you end up with a Voronoi diagram. And because you can refer to this triangulation as a graph, this is the dual graph, so the opposite graph, so to speak. This is easily constructed from the delaunay triangulation, and fortunately inside of Houdini there is a node that can just compute this dual graph, this Voronoi mesh, out of a delaunay triangulation. And we want to use this inside of Houdini to do a pretty surface treatment to an object. So let's dive in and get started. So first things first, let's lay down a file object and dive inside. Inside you will find a file sub. And we want to load an object that I created for this tutorial inside of 3D Code. You can use this object, it comes with the downloads, or you can use your own object. Just make sure that the curvature of the object is varying smoothly. So I will import my object called basemesh03 obj. And it comes in huge because stuff in 3D Code uses a different coordinate system. So let's transform it by using a transform node, and let's scale this down to 0.01, like so. Now, this is the object I created, and if you look at the mesh, you see that the mesh is quite ugly, and that is because I used voxel sculpting, and that is an iso surface created by using margin cubes, and that is definitely not a delaunay triangulation. Fortunately, we can create a delaunay triangulation directly inside of Houdini by using the remesh sub. So let's append a remesh sub here, make it visible, and wait for it to compute. And you see you are getting this. Looks a lot like a delaunay triangulation. The triangles are very even. Let's go down to 0.02 to have more triangles. And here you have the delaunay triangulation. To make the effect a little bit more interesting though, it would be nice if the triangles wouldn't be all the same size. Fortunately, we can just drive the size of the triangles by an attribute called targetmeshsize. We first have to set it. So let's use a warp, a point warp in this case, a point warp before the remesh. So let's make the transform visible and add this point warp, and let's call it set targetmeshsize, like so. Make it visible and dive inside. Now inside I want to use an anti-alias noise to just get some random values on the surface, and then I want to fit them to set the target mesh size attribute. So let's start with an anti-alias noise. Let's connect the position and let's see what this gives by wiring it to CD. These very dark areas indicate that the anti-alias noise is going into the negatives, so let's append a fit node. Connect it here. Let's make the source minimum minus 0.5 and the source max 0.5. That is roughly the range that the anti-alias noise is outputting in. And let's transform this to 0 to 1. Now the dark areas are gone, but we want a way of shaping this noise. So let's lay down a ramp parameter. Switch this to be a spline ramp because we are dealing with floats here, and connect it after the fact. Now everything turns black, and that is because if you go one level up, you see this ramp defaults to 0. But if you open this up and just move this second knot up, you see that we have our values back. And now you can just say that this noise should be a little bit more steep, or the transition between white and black should be more steep, like that. Nice. Now we can go into the anti-alias noise and maybe up the frequency to 3. Well, 33 is a little high, 3, like so, and that gives some nice random values. But after the ramp, we are confronted with values between 0 and 1, and the target mesh size has to be different. So that is why I use a second fit. Fit range takes in a range between 0 and 1, and outputs a different range. I want to be able to dial in these values on the operator itself, so I right click on destination min and say promote parameter, and same for destination max. Like this. So what I can do now is to dial in the values here. Values that might work is for the minimum value 0.01 and for the maximum value 0.1, like so. Of course, with color, that makes not too much sense. So let's dive in, cut the connection to color, and instead lay down a bind, as we want to export this to a new attribute. And this attribute is called targetmeshsize. And that is a special attribute as it is understood by the remesh. So now that we have this target mesh size in place, let's check if this is actually the case by creating a color visualizer and just visualizing target mesh size, like so, a rammed attribute, and you see here we have the target mesh size. Now if you make the remesh visible again, you see that nothing changed, and that is due to the settings of the remesh. So go to the remesh. At the moment the element sizing is set to uniform. We want to set it to adaptive, and as soon as we do that, the remesh recooks and it will eventually change its interface. And now you can just open up this control attributes drop down and tick mesh size attribute, and here you see target mesh size. Of course, you could rename it, but let's stick to the defaults, and you see that we now have small and large polygons here. The small ones are probably a little too small. We can easily change that by going here and upping this to 0.02. Let's wait for the recook, and here we have it. Nice distribution of large and small triangles. Now that we have that, it's time to create the dual mesh, the dual graph. And we do this by using the divide node. So append a divide node after the remesh, make it visible, and check compute dual here. And you see now this creates the dual diagram directly. Simple as that. The basic structure is in place. Now we want to extrude the individual facets, but we don't want to extrude all of them. We just want to create crackles on the surface. These crackles only look interesting if I don't create them all over the place. That is why I want to use a measure to decide where to use these crackles. And the measure that I want to use is curvature. Lay down a measure sub and append it here, make it visible. And if you switch to the handle tool, it directly shows you the visualization. At the moment it's computing area. Instead we want to compute curvature, and we want to go for the mean curvature. By default the measure sub is set to calculate the value on primitives. We want to calculate it on points instead, which gives us this. So now you see that you have concave and convex areas indicated by blue and red. Due to the nature of how the curvature is computed, this is not very smooth. So to make it smooth, let's append an attribute blur, and let's blur the curvature. To see what we are doing, let's create another color visualizer and call this one curvature, and the label should be curvature. And the attribute to visualize is curvature, like so. Rammed attribute, close, and now if we deactivate this, well, we have to actually go to center and width, like so, and if we decrease the width, you see that we get our visualization back. And now we can go with the attribute blur and use curvature as the attribute blur. And we want to blur it with 2 blurring iterations to give a quite smooth curvature, maybe even 3, like so. Now that is the curvature that we want to decide where to cut the mesh open, so to speak. To do that, we want to use a node called vertex split. The vertex split node decides where a vertex attribute crosses a threshold, and where this is the case, it will just cut the mesh open, duplicate the points, and open up the mesh, so to speak. So to be able to do that, this attribute, curvature, that is currently on points, has to end up on vertices. So we could in theory just promote it to vertices, but that would mean that the vertices on one polygon would have different values as the attribute is currently on points. So let's do a trick and first promote the attribute to primitive level, making sure that each polygon gets the same value at all of its corners, and then promote it to vertex level. So let's put down a promote, attribute promote, and let's promote the curvature to primitive. Curvature. instead of Curvature. And you see, now this makes sure that each polygon gets the same value throughout. Let's change the name, as you might want to use the original Curvature in shading later, and tick off delete original, and the new name should be Curvature 2, like so. And now, of course, I see the point attribute again, so let's update this, visualize it to Curvature 2. Now we have it on polygons, and now let's use a second promote, attribute promote, to transfer this attribute, Curvature 2, from primitive to vertex level. Not much changes visually, because now it is on vertices, but as every poly has a vertex in the corner, the distribution remains the same. But now that we have the attribute on vertices, what we can do is to introduce a vertex split. And this vertex split splits the mesh open. We can see this if we switch to smooth shaded, and you can see at the moment the mesh is entirely smooth. But if we now use the attribute Curvature 2, it gets split. That of course breaks the shading. But as you can probably tell, it gets split everywhere. And that is because the tolerance is too low. The tolerance decides how far of a change of an attribute the node has to detect to create a split. So go up with this tolerance value until you get a nice distribution of splits, as you can see here. Now, if I go to 0.03, say, I have areas that are still smooth and areas that are split. It's hard to see, but I think you can figure it out by just moving the object around. So now that this object is prepared, we can go to the last step, and that is extruding the surface and throwing it into a subdivision surface. To extrude the surface, let's create a poly extrude, and append it here. And let's say we want a distance of 0.02, like so. You see, now that we created this, that it extrudes all the polygons along the edge normals, or the primitive normals, and that means that these crackles now start to show. So in the areas where the mesh is cut open, the normals are different, and that is why these crackles show up. If you switch over to smooth wire shaded, you see that we just have one extrusion. Now we can append a subdivision surface to smooth it out, but that gives a very smooth result. I mean, it looks interesting. Let me switch to smooth shaded again. It's very, very organic, but probably we want to flatten the top of the extrusion. So that is why I use a second poly extrude and append it here after the first one. And this one should extrude everything again by 0.002 to create just a little second extrusion. At the moment, it is creating the extrusion everywhere, and that means even on the sides, on the extruded sides, which leads to these artifacts. How can we avoid creating these artifacts? Well, with the first poly extrude, we can output a group. Let's output a front group called extrude front. And then let's say that the second poly extrude only operates on this group by putting it here in the group field, extrude front. And that means that it's now only extruding the front faces. And that gives just this nice little edge loop here. And if you now switch to the subdivide node, you see that everything is a lot harsher. Let's up the subdivide depth to 2, like so. And if I now switch to smooth shaded, we got this beautiful result where you have these very organic structures that remind me, I don't know, of reptile skin or something that grows underwater. And by varying the threshold, you can of course decide how much of these crackle structures you actually want to have. So that concludes how you can create this interesting dual surface treatment to any object by just using standard Houdini nodes without any VEX. To render this, I used a dirt shader in Octane, where I inverted the normals to just emphasize the edges, and then I just used a switch node to switch between two materials to make the edges metallic and everything else diffuse. That is basically it. So I hope you liked this tutorial and learned something, and see you next time. If you like what we are doing, please consider becoming a Patreon for supporting us and for access to more in-depth courses on topics like volume techniques or PDG or vellum and more. To everybody who is already supporting us, thank you so much. Without your continuous support, Entagma would not be possible.